Okay, so today we're going to be talking about mixtures. It's the first time we branch out to beyond one component. Think about all the stuff we've done so far, the engines and everything, most of our partition functions and so on. Although for partition function, we did do some reactions. We had like generic A plus B type reactions, but here we get into the physical properties of mixtures, and it gets interesting. I wouldn't say it's much more difficult, but it's interesting. So let's jump in. So let's first talk about whether mixing is spontaneous or not, and there's some vocabulary words that we use. We use ideal, solutions, and so on. So let's unpack that a little bit. So the Gibbs energy of mixing, first of all, let me just write Gibbs energy. You guys know this from the previous sets of notes, but Gibbs energy delta G, just as a reminder, is equal to delta H minus T times delta S. Ring a bell? Okay, so notice this minus T delta S, that favors mixing because spontaneous delta G's are negative, right? So if we get a negative delta G, then we're guaranteed to have a spontaneous reaction as written. And for mixing, we have component A plus component B, I would say independently, right? A, and then we're going to like A plus B all mixed together. Do you see the brackets are kind of to indicate containers? There's really not a very easy way to write this, but you've got two unmixed substances, and then in the products is mixed substances. But there's no chemical reaction. It's just mixing. Think of if you had taken the time to segregate all of the little colors of your jelly beans or your M&Ms, you have them all nice and neat layers, and then your niece or nephew comes in and grabs the jar and shakes it. Yeah, it's going to mix, right? It's not going to stay unmixed. And the reason it mixes because there's no attractions between the particles that you have to break. But with molecules, we have attractions between the molecules, and we have attractions to molecules to themselves, and we have attractions of molecules to the opposite or other mixing partners that you have. So if there's no attractions at all, then that's a delta H of mixing of 0. There's no energetic penalty to mixing. So that's the marbles in a jar, that's the M&Ms in a jar. There's no energetic barrier to overcome, and that's an ideal situation. So that's what this delta H of mixing, if there's no intermolecular attracting differences between the molecules attracted to themselves or molecules attracted to their mixing partners, then their delta H of mixing is 0. It doesn't mean that there's no attraction, it's just that there are no differences between reactants and products. So it takes as much energy to pull the blue M&Ms apart as it does the green ones. And then when you mix them together, it has the same attraction as it did to themselves. There's no difference. So that's the ideal situation. And that's what we have when we have really small London dispersion forces or like particles. So think about, well, really it's anytime the attractions are similar. So this could be benzene and toluene, where they both have London dispersion forces and they're fairly weak, but it could also be strong forces like water and hydrogen bonding if the other component also has hydrogen bonding. So think of methanol. Methanol has the OH, water has OHs. You can mix them in all proportions because the differences between the hydrogen bonds are minimal. And if delta H of mixing is 0, then it's spontaneously going to go together. Why is that? Well, think about the entropy. Now, when we do have substantial differences in enthalpy of mixing, there's a bunch of different models for that. One of which is the Hansen solubility parameters. So we have a lab on that the week after spring break. So I don't have a lab right after spring break. It can give us a chance to ramp up. And then as also in case we had a snow week or something where we'd wipe out a lab, it was a week to catch up. So we'll talk about and do the Hansen solubility parameters lab 2 weeks from now. So let's talk about entropy. If you look at the entropy of mixing equation, and this is from England Reed's PChem book, page 202, it's the mole fractions, and so we'll discuss these mole fractions. But these right here, this is x, or I say n, so that should, so this is number of moles of substance I divided by n total. Well, think about that. The max that can be is 1. If I have a single component, then it's 1. If I have any kind of mixture, it's less than 1. So all of those xi's are less than 1. And because of that, then all of those natural logs are negative, because the natural log of a number that's less than 1 is negative. And so that cancels the negative sign, so all of our entropy of mixing is positive. So in all mixtures, you have a positive entropy of mixing. And that's nice, that's intuitive, right? That's your niece and nephew shaking the jar of M&Ms. It's gonna mix. So it's just statistics, right? And think about it too from a gas phase point of view. Like if you have all of the blue M&Ms in the bottom of the jar, the volume is small. And then if you sort of allow them to take the whole volume of the container, then the volume is big. And we know just from the partition function that if you expand the volume, then the energy levels collapse and you have a higher population and a higher entropy. And so, you know, this your intuition should govern here, that mixing is spontaneous, as long as there's no energy barrier. If there's an energy barrier, then you can't get like oil and water to mix at room temperature, because that energy barrier keeps them apart. It takes so much energy to pull water apart that when you stick oil in there, it doesn't give you anything back. And so it's just not, oil is not able to tear water apart. So let's say we did that artificially, like we sprayed steam into oil. It will be like an emulsion after a while, but after a while, as soon as the water molecules move around and they slip past an oil molecule and snap together, that oil molecule is never getting back between those two water molecules. And so it just slowly pushes the oil out. And if the oil is less dense, it goes to the top. If it's more dense, it goes to the bottom. But the point is there's separation, spontaneous separation. So we put these together, and if delta H of mixing is 0, then the delta G of mixing is just the entropy of mixing, and so that mixing is always spontaneous for these ideal solutions. Okay. All right. Now, Gibbs energy change at equilibrium. When things are at equilibrium, then all portions of the container have the same Gibbs energy. And so, you know, the Gibbs energy is set to 0 at equilibrium. We've done that before. You have the standard Gibbs energy. That's how we kind of get to the equilibrium constant expression. And so we call this molar Gibbs energy. You might hear the term chemical potential. So all through the chemistry text and in the literature, you hear them talking about chemical potential. And I like that term, but I also like Gibbs energy. So I typically stick to Gibbs energy, but I want to point out the chemical potential because it's really nice to think about this as potential energy. You have a ball on a hill as a high potential energy. If it starts to roll, it spontaneously rolls down the hill. Same with the chemical potential. If I have reactants that are way up here, that spontaneous rolling down the hill is that reaction going in the forward direction. So Gibbs energy is chemical potential. It's how much potential that chemical mix of reactants has. It will roll downhill spontaneously without any external support or external influence. You might need to get it started. There might be a little activation energy, but then once it goes, it goes. Okay, so now here's some essential terms when we start mixing things. I've already used one of them. I used the mole fraction. And so we use X, Y, and Z, and they have particular meanings. So X is used to designate the mole fraction in the liquid phase. Okay. And then Y is used to designate the mole fraction in the gas phase. And then Z is used to designate the overall mole fraction in the container. And so you asked about the lever rule. I'll draw that here a little bit. So let's say we have a line here that's the liquid line. And over here is a line for the gas phase. And then we had the overall composition in the container is ZA. And we would draw a horizontal line across here and treat the Z line as the fulcrum. And so did y'all ever play with the seesaw? Did y'all ever have a seesaw when you were kids? I mean, I always have to ask that because, you know, they made playgrounds all safe and everything. And so, you know, if you were, like, when I was little, we would go to the ballpark and it was a great seesaw. And, you know, if you were, like if you had an older friend, one guy that was bigger than you and you wanted a seesaw, it wouldn't work if you both sat the same distance from the fulcrum. And so like in my little scrawny self, I was over here on the end, okay? And my big buddy would be real close like this because he was a chunk. Okay, that's my buddy. Right? And so the distance from the line is like the opposite of the mass, right? So this distance here is related to his mass, and this distance here is related to my mass. Makes sense? And so it's the number of moles, so the number of moles of particles in my buddy here, so NA, and this is length A, is equal to NB times the length B. So that's the lever rule. And so you could rearrange this where like NA over NB is in it and is equal to LB over LA. So that's another way to write it. And notice that, yeah, my little mass over here on the right is associated with the short length of B, and vice versa. You know, the big mass is directly across from the long length. So that's the lever rule, and that applies in that phase diagram region where you had liquid vapor. It also applies in that phase diagram region where you had solid liquid. So anytime you had two phases in equilibrium, you have the lever rule region. And that's what we have here in between liquid and gas. So let's look at some of these phase diagrams where the lever rule applies. But first, let's talk about the mixtures. So when we put two components together, we need to describe our axes. In this case, we're looking at the pressures. This is a phase diagram, so now this is a PX phase diagram. X meaning mole fraction. Can I get you to shut that for me? Thanks. So it's a pressure versus composition. Now, where's temperature? Where's volume? Well, this is for a particular volume and a particular temperature. So now it's really frustrating because we were able to print a 3D model of the PVT phase diagram for water. We had a pressure, a volume, and a temperature for a set number of moles. We printed that diagram, okay? But now we have a mixture. And so we've taken every one of those axes and added an axis to it. So for the temperature, we have a TX phase diagram. And for the pressure, we have a PX phase diagram. And for the volume, I've never seen it, but I guess you can make a VX phase diagram. But I've seen PX and TX, that's what we're going to cover. So let's look at the pressure composition phase diagram. Now down here, we have the mole fraction. Mole fractions are super easy to think about because we have the mole fraction of A. So over here, this is 100% A. And over on the left is 0% A. Now 1 minus that is percent B, or 100%, you know, 1 minus that times 100% would give you the percent B. So over here, this is 100% B. And this is 0% B. Does that make sense? Okay, so we understand the axes. Okay, so if I have, over here I have 0% A, and over here I have 100% A. This is the vapor pressure of pure A. Pure A, I always think of a blender when I see that. Okay, so, and then over here is the vapor pressure of pure B. Because if you think about that, that's the part of the phase diagram where all you have is B. And so at this temperature, that's the pressure of B, the partial pressure of B in the container. In this particular situation, the vapor pressure of pure A is above 1 atmosphere. So this, this is a low boiler, I guess. And then Roult's law. Think about Roult's law. It's such a simple equation just to think about. The vapor pressure of A would just be 0 at, if you have 0 A, there's 0 atmospheres of A. If you have pure A, you have the pure vapor pressure of A. Let's just draw a line between those 2 points. And that line is this right here. It's the mole fraction of A times the vapor pressure of pure A. So that's Roult's law. And so Roult's law are these 2 lines right here. So this B does the same thing. Over here, it's 0. So the mole fraction of B times the vapor pressure of B. So it's 0 on the right all the way up to the vapor pressure of pure B on the left. So the Roult's law is this X in the middle. And then Dalton's law is the sum of those 2. So Dalton's law is right here. Roult's law can fail. Like we just drew a straight line between those 2 endpoints, and the vapor pressure of A or B may not be that straight line. So Roult's law can fail, but Dalton's law doesn't. Dalton's law is just the law of the universe. If you've got a box full of molecules bouncing around, the pressures add up. Because it's just the wall of the container, and it's the pressure of A hitting that wall, and it's B hitting that wall, and you just add them up. So Dalton's law is ironclad, and we use that to solve a lot of these problems. But Roult's law can fail. Okay. Okay, it's nice to have a law that cannot fail. It's the only one, I think. Okay, so let's jump in. It's temperature dependent. So just like the Claussius-Clapeyron equation can change that vapor pressure of the pure substance, or the Antoine equation can change that pure substance vapor pressure, that means that every one of these px phase diagrams is temperature dependent. So if we change the temperature, that line moves up and down and so on. So I'm just showing the Dalton's law line, kind of showing what happens as I raise the temperature for both of those. We've got 3 temperatures listed. Now what's kind of interesting is at 270, that's the boiling point of A. That's when pure A vapor pressure is 1 atmosphere. So this is this line here, this normal boiling point line. And so then this is the normal boiling point for this composition. What would you say that is? This is 50, that's 75, 60, so about 60% A. So look at the temperature of that yellow line. It's 280 degrees. So that composition boils at 280. If it's pure A, it boils at 270. You mix them together, it kind of makes sense. B is a lower boiler. I mean, as a higher boiler. So you mix in B and the boiling point creeps up. And so that would boil at 280. Over here, this is 298. This is what about? This is 25, 35. No, let's see. What would you say? 30. So this is going to be 30% A and 70% B. Since B boils at a higher temperature, we mix more of it in there, then we raise that boiling point even higher. So this is boiling at 298 Kelvin, and it's a 30% A. So it all should kind of make intuitive sense. You've got B that is boils at a much higher temperature. So we're mixing in B, and we're raising the boiling point of the mixture. This will be a lot easier to follow when we get to the TX phase diagram, but I just wanted to kind of hint that they have the same information. All right, let's look at the vapor phase composition line. So this one is kind of a brain bender. It's on the x-axis, we have two labels. We have XA and YA, and I've got a red box around YA to indicate that that red line is the YA, or the vapor composition line. So this one is this line right here. So the compositions of the liquid phase and the vapor phase, underline, are not the same. If they were always the same, we could never distill anything, because that's how distillation works. You heat something up and the vapor is more rich in something. It's more rich in the lower boiler. So the lower boiler is leaving and leaving behind the high boiler. And that's how distillation works. And that's because the vapor pressures aren't the same. These Roult's law, they have different pure vapor pressures and they have different compositions in terms of their Dalton's law. And if we were able to get it to distill a whole bunch of times, like in a fractioning column, then only the most volatile substance would make it to the top. And you'd have them come off at pure compound one at a time. Yeah, so this is really cool. Because the vapor phase composition is different than the liquid phase composition, we're able to separate mixtures. And so this map of pressures and compositions at each phase, at which each phase is stable, is this phase diagram. Oops, let's go back. Now, we could also have put on here ZA. Let's see. Yeah, so the XA line is this one up here. And the overall plot is plotting ZA. So how do I mark that? Let's see. Come on. PowerPoint's not letting me draw that close to the bottom. Let me just mark up that. So I'll put ZA. So let's say a 50-50 mixture, ZA. I'm going to draw a vertical line here. Oh my gosh. Trying to draw straight on this thing is so hard. Okay, so I'm going to get right here. I want to go like this. I need a ruler. Okay, so if we say we're at a 50-50 mixture in the container, up here, if I'm at that point, it's all liquid. When I get to this pressure, I'm right at all liquid, but a little bit of vapor shows up. So at that pressure, the vapor has that composition. If I'm at this pressure, I have about equal moles in the vapor and in the liquid phase. And then if I'm at this low pressure, I have almost all vapor. And then down here, it's all vapor. So in this region here, that's called a two-phase region. Where we have to use the lever rule to figure out how many moles are in each phase. If I'm above that, it's all liquid. If I'm below that, it's all vapor. So the interesting piece is in that two-phase region. That's where you have a boiling solution. Okay. We'll do some more with that later, so if that's still a mystery to you, that's okay. So here's, again, just, I guess, more of the same. What I've drew on the previous figure is essentially the same. Okay. So let's look at dissimilar liquids, at some non-ideal solutions. So this is carbon disulfide and acetone mixed together, and it's crazy looking. Okay. So there are substantial deviations from the ideal partial pressures. And remember I said that you can have Roult's law fail. Well, this is a case where Roult's law has failed spectacularly, but Dalton's law has not. So you've still got this partial pressure for acetone, this partial pressure for carbon disulfide, but they add up to this pressure. So that's the Dalton's law line up here. So this is still, P acetone plus P CS2 equals P total. So Dalton's law still hangs on, and we have that crazy curve at the top. Now, why might this be? Well, think about the intermolecular attractions and so on, and they if the molecules are really different, like water and oil, there's a tendency to exclude the smaller component. So water can snap together, and the oil has no place to go, so it wants to leave. Same thing with carbon disulfide. Acetone is very polar. Carbon disulfide is not polar at all. So if you put a little bit of carbon disulfide in acetone, it's going to be excluded and have a really higher vapor pressure. If you put acetone and carbon disulfide, really the carbon disulfide is such a big floppy molecule, it will exclude the acetone. It doesn't do anything with the polar end of that molecule, the carbonyl, and so it just excludes it. So you put a little bit of acetone in carbon disulfide and it leaves. They have a lot of time to interact. And so we have to come up with a new observation. And again, when we talk about laws, remember those laws are just observations. They're observations of the way nature works. So a lot of times we have this connotation in our mind that a law is something unbreakable, or that the law is somehow higher than a theory. It's exactly the opposite. The theory is the thing that is trying to explain what's happening. The law is just the observation. And so these are some really simple laws. They're just linear laws. So let's look at this Henry's law and compare it to Roult's law. So remember, Roult's law was the simplest thing. You just took the pure vapor pressure and zero and drew a straight line between the two. Well, in Henry's law, we take the dilute region, and since dilute regions of B are dominated by the presence of individual B particles. And so now down here we have the mole fraction of B. So this is 100% B. So that means this is dilute over here. So that dilute region is over here, and that's the region where we use Henry's law. So if we were to take a couple of measurements of the vapor pressure, the partial pressure of B at really dilute concentrations, and then I'm going to try to use this ruler. I don't know how this is going to work. How will I find, let me find it right here. Okay, I'm going to put that down right there. I need 3 hands. Okay, so I need to raise the slope. almost. There we go. We're getting it. All right. Okay, here we go. So we take this data point right here and just extrapolate. Oh, let's change this. Oh my gosh, even more slow. This is a really non-ideal solution. Yeah, here we go. There's my ruler. So we're just extrapolating from those few data points all the way to the other side, and that's the Henry's law constant. It seems crazy, doesn't it? I mean, we're not learning, with the Henry's law constant, we're not learning anything about the far right side. We're only learning about the far left side. But it gives us an idea of how it behaves in terms of dilute solutions. Now, this is most often used for gas concentrations in liquids. So think about your lake waters and so on. You want to know how much oxygen the fish have to breathe with in that lake water. The Henry's law constant of oxygen in water is what they use, because that's the concentration of oxygen in water, and it's temperature dependent, right? So we can map that out. We can have a Henry's law constant that's temperature dependent, and we could calculate the amount of dissolved oxygen in water. So that's a dilute solution. So that doesn't tell us anything about water and pure oxygen. Okay, it tells us about the amount of water, oxygen that's going to dissolve in this solvent of water. So that's atmospheric gas concentrations in waters, blood gas concentrations, CO2 in an aqueous system like your blood. All of these are great Henry's law situations. And so you can look up those Henry's law constants and calculate those really dilute concentrations in their vapor pressure concentrations. The concentration area of B, that's where Roult's law applies. And so look at the behavior of that line, the dark line. You know, it comes in and it converges with that linear line. And so this is just showing you the slight reduction in vapor pressure of B when you mix in an impurity. Okay, so you mix in a small impurity and B's vapor pressure drops a little bit. And that's following Roult's law. Instead of it being 100% pure B and its boiling point or its vapor pressure, you mix in 5% impurity and it's going to be 95% of its pure vapor pressure on a mole basis. So the partial pressure of the solute depends upon the mole fraction of the solute, but that proportionality is not the vapor pressure, it's the Henry's law constant. So if B is the solvent, we use Roult's law. If B is the solute, we use Henry's law. And those equations can't be any simpler. It's just the mole fraction times some constant, right? And then, of course, ideal solutions, the Henry's law constant and the pure vapor pressure are equal. So that's how you can kind of tell how different or how non-ideal a mixture is you've got the pure vapor pressure, and the Henry's law constant is in the same units. It's an atmosphere or a torr or something like that. If it's dramatically different than the pure vapor pressure, then you've got a non-ideal solution. If they're very close to each other, then you have more of an ideal solution. So here's a tale of two mixtures. They don't always have to hate each other. Okay, so carbon disulfide and acetone are not BFFs. They do not want to hang out together. They want to be out of the solution. Whereas chloroform and acetone do like each other. Now, why might that be? Well, you've got chloroform. And it's so easy for it to interact with this carbonyl on acetone. And because you have that nice interaction, about close to a 50-50 mixture of these two will have the sweet spot of interactions. And so you can see the vapor pressure of the mixture drops around 50%. It's a little higher, but around 50%, that's the low point of the vapor pressure. So in this case, if I wanted to hold on to chloroform and hold on to acetone reliably, I could mix them together and they would hold on to each other, and I wouldn't lose as much to evaporation. And here, this is a situation, let's look at the Henry's law lines. So notice the Henry's law constants are less than the pure vapor pressures. So there it tells you when you have a solution that's attractive, the mixture is attractive or more energetically favorable. Over here, the Henry's law constants are completely off scale. They're out, you know, if I were to extrapolate that line, it'd be past the roof of the building on this scale. Okay. So it could go either way. They could hate each other or they could love each other. And so that's what we have with non-ideal mixtures. This is just showing you the molecular view. You just think about, you know, the dilute solutions, you know, like if this is that acetone and this is carbon disulfide and it's near at the surface and it doesn't like its nearest neighbors, then it's easier to leave. Okay, whereas acetone bonded to acetone with the polar components, it's going to be harder for acetone to leave. And so it's just showing you the molecular view. Here's the actual data for acetone and carbon disulfide. And it has these things called activities. So if the mole fraction doesn't quite tell the whole story, okay, then we need to put some correction in front of it. And so we have these things called activity coefficients. So this right here. Okay. And gamma A is a function of XA, right? You can see that we saw for gamma A, it's this function of XA. So it's dependent upon the mole fraction. You can use it to calculate the activities of the solution. And activities serve a lot of useful purposes in chemistry. You could think of it as an approximation to the partition function. Remember, we solved the equilibrium constant as a function of the partition functions. And we said that all of the other equilibrium constants you had dealt with in the past were approximations. So the partial pressure of a substance was an approximation of the partition function. The concentration of the substance, like we write a concentration equilibrium constant, that concentration is an approximation of the partition function. Here we're showing that the partial pressure is not accurate enough even for our pressure diagrams. So it's a correction for the pressure diagram, but it's also would be activity coefficients would be a correction for that equilibrium constant expression. So activities really figure in when we're trying to deal with real solutions, real mixtures, real reactions. Now we can model these really strange curves with this exponential function. I'm really just showing you this to kind of show you that we do have some models for it, but we don't really get into that in this course. It's beyond the specific, you know, the level of rigor that we have for this course. The corrections of these vapor pressure curves gets incredibly involved. If you are interested in that, I had a master's student write up sort of a summary of all of the literature on modeling these curves about 5 years ago, Nilan Kamathwada, and his project was trying to find azeotropes of solvent mixtures and cleaning formulations. And he got into all these different equations, and it was detailed. I had a hard time even advising that thesis because he was digging so deep into the literature, and him trying to explain it to me, I was like, oh my gosh, you gotta be kidding me. So it was just correction after correction after correction, and the literature was very fractured. You had Wilson's constants and Margulies values, and everybody was using a different model. So it was totally difficult to figure out which is the governing model for this. He did a great job, but I mean, he made his equations out in an Excel spreadsheet and everything was color coded. It's like, this is this person's model from this paper, then we correct it with this person's model and this person's model, and he got it all worked out. But man, it broke my brain. Yeah. And then here's again a more detailed picture of what I showed with the lever rule. When we get to the TX phase diagram after spring break, we will do a lever rule calculation. Okay, so If you don't quite get the lever rule yet, you're just sort of at the swing set model or the seesaw model, that's okay for now. All right, we'll talk to you then. Have a great spring break, and just behave. Relax. Hopefully you catch up on your reading.